Let's get her done. The last two problems. Here we go. The last two problems and the last two problems in the force unit. This whole force torque equilibrium thing. This is it. Two more to go. Hang in there. You can do it. I have faith in you. Those last two problems are equilibrium problems, but they're not torque equilibrium problems per se. They are force equilibrium problems. Force equilibrium? What do you mean? Well, let me give you an example of a force equilibrium problem. It's not the last two on the sheet. It would be this. I push this way, you push this way with equal and opposite force. That would be a force equilibrium problem. I mean, there are forces, and it's not accelerating, so it's in equilibrium. Simple, right? Yeah, simple. Okay, yeah. We'll take a look at those last two problems and see if those are simple and how to do them, because they are still force equilibrium problems. All right, here we go. Number 5. A traffic light weighs 800 newtons. It's held up over a street by two cables. Each cable makes an angle of 30 degrees with the vertical when connected to the street light. So let's draw this out. So we have street light. And we have two cables holding that street light up. Okay, for a little more stability instead of just one cable dangling in the wind there. And so these are attached to something up here, whatever, metal pole or something. And we have the angle, okay, and it was 30 degrees, I believe, yep. The angle with 30 degrees with the vertical when connected to the street light, or a 60-degree angle when connected to the post. Okay, so what that means is here's the vertical, there's your vertical, and these are 30 degrees. And that would be a right angle, and those are the 60 degrees connected to that pole. So you have a 30, 60, 90 triangle. Special. All right, now let's see what the question is. What's the question? How much tension do each of the cables have in them acting on this light? So in other words, we are holding up this light, which is 800 newtons. Okay, pretty heavy, by these two cables. And the question is, how much tension do each one of the cables have? Now, tension is just another word for force in a rope or a chain or a cable. And it's just a word for force. So tension just means how much force do each one of the two cables have on them supporting. Now, you might be tempted to say, well, this is easy, right? Because it's 800 newtons. We're holding up 800 newtons. And each one of the cables is exactly at 30 degrees. Okay, now it's some kind of a funky angle going out here, so each one's at 30. So logic would say they both hold up half the weight. So each cable must be holding up 400 newtons. No, come on. You know it's not going to be that easy. No, actually it isn't. They're going to actually be holding up more than the 400 newtons each for the total of 800. Well, that doesn't make any sense. How can, okay, because here, think about this. Let's say that you're lifting up. Let's say you're Jack and Jill. Jack and Jill went up the hill to fetch a pail of water. They go up, they get the pail of water, and they're walking down. Before Jack breaks his crown, okay, they're walking with their pail of water. How are they carrying that pail of water? Are they holding that pail of water in their hand right down by the side, or are they going to hold it out like this? Would you walk around with a pail of water like this? Maybe you would if you're trying to build muscle. I mean, you're doing a workout, but most people would not be doing that. That's difficult to do. You know that. So even holding your arm out on the side, if you keep doing that, you're going to get tired, and eventually you're going to, because you're applying more force. The muscles have to apply more force, more tension when you're putting something out at an angle. Because what you're doing is not only are you, so if I have it, my arm is next to me like this is nothing. I can do this all day, okay? Because gravity's just pulling down on it, and that's it. But now I've got to put tension in my arm to keep it up from the ground, to lift it up against gravity, and to hold it out. So I'm doing two things at once. I'm lifting it, and I am holding it. So I'm doing a lift and a pull. There are actually two motions involved there. And there are two motions involved with each one of these cables. These cables aren't directly 90 degrees like this. If they were, if we had two cables at 90 degrees like this, but if the two cables were like that, yeah, 400 each, game over, man, game over. But they're not. So that means that these cables are not only pulling up on the light, they're also pulling out on the light. Yes, imagine if one of these cables snaps. Imagine this one snaps here. Boom. What would happen? It would rotate in this direction. And the reason it would do that is because there's a force in that direction. You can't move or accelerate in a particular direction without a force in that direction. Which should mean that if this cable breaks, it goes zoom. There's a force in that direction causing it to happen. So this cable is applying two forces at once. It's applying a force up, and it's applying a force to the left, everything you own in a box, to the left, okay? I got lyrics, okay, I got lyrics. So, because of that, because of the two forces being applied to the light by each cable, the up and the over, there is more than 400 newtons being applied. So it's a combination of up and over, more than 400 newtons. It becomes the hypotenuse of a triangle. Now, here's what we do know. We do know that each cable is holding up equal amounts of the 800 newtons. So it is true that the cables in the upwards direction are holding up 800 newtons, and therefore they split that equally, so 400 newtons. This cable in the upwards direction is holding up 400 newtons, yes, in the upwards direction. But we want to know what that is right there. All right, so we can break this down like this. I'm going to redraw this with just one triangle. I'll just take this one triangle, take this angle, we'll take this out. Take this out. Let's just focus on that cable there, because that cable is going to have the exact same tension or force in it than this cable is, because they're at the same angle. So I hope we agree on that, right? So if I just figure out what this cable is, that X there, I know what the other one is. Okay, so here's what I know. I know that the two cables are working together equally angled to hold up 800 newtons. That means each one will be responsible for 400 of the upward newtons force, of the upwards newtons force. So each cable is holding up 400 newtons in the upwards direction. Well, there's your setup. Now we can go ahead and solve for this side and figure out how much tension is in that cable. We know that there's 400 newtons per cable in the upwards direction, and that's 30 degrees. I'm going to use my cosine. Again, triangles never go away. Cosine of 30 degrees times 400, and we'll have the answer to this problem. Let's go ahead and crank that out. So let's do cosine of 30. And that's going to be cosine is equal to the adjacent over the hypotenuse. So let me show you this, though. This is going to be different than what we usually do in terms of the setup. Cosine of 30 equals my adjacent side, 400, divided by hypotenuse x. So be careful here. Usually we end up finding the adjacent side and multiplying. We're not multiplying this time, we're dividing. So there's going to be 400 divided by the cosine of 30, which is 0.8660. So you go ahead and do that. You go ahead and do that out and see what we get. So we get a number bigger than 400. That will make sense. We'll explain that in a second here. So that's 400, 0, so 462. So the answer, x equals 462 newtons. Remember, that should make sense. We should get a number over here. It's larger. It's the hypotenuse 1. And we're pulling not just up with this cable, but also over at the same time. When you lift your arm, you are not just lifting up on the arm, which you are doing. There's an upwards motion, but you're also pulling the arm in, and that certainly is. As a matter of fact, if gravity were to just kind of quit, then you would just, gravity's not holding up, because you are pulling back on your arm. You don't want your arm to run away from you. So there's more tension when you do this. Right? You know that there's more tension out here. So therefore, that's harder than that is. So if that's harder than that is, there has to be more force applied. And your body eventually says, I'm tired of doing that. And you're probably saying, I'm tired of doing this problem. Okay, can you move on to the next one? I will. The other cable, set up exactly the same way, would have exactly the same amount of tension. 400 up for the two cables. That's a total of 800, holding up 800. That makes sense, but at an angle, going to be greater than the 400. Okay, let's get that last problem done. Now, this is a, if I remember, a street sign. Yep, street sign. It's being held up by two cables, all right, and the drawing looks like this. So let's get this drawn out here. And we're holding up this street sign with this cable labeled T2, meaning tension 2, and this cable is T1, meaning tension 1, and there's an angle there like that. All right, okay, and the question here is how much tension is there in each one of the cables holding up the sign? 600 Newton sign. So that means 600 Newton sign. And this is an equilibrium problem, as the last one was. So you think back with the last problem, you had the street light, and it wasn't doing anything, it was just sitting there. It wasn't moving, it wasn't moving up, it wasn't moving down, it wasn't moving sideways. Okay. Those are called translational motions, up, down, and sideways. So it wasn't moving translationally, it was an equilibrium up and down sideways, and it wasn't rotating. It wasn't spinning around. If one of the cables breaks, it would begin to do a rotational motion, but it wasn't doing that, so it was an equilibrium. So therefore, it's not accelerating, sitting there, equilibrium. Same thing here. It's an equilibrium. How do you know? It's not going anywhere. So it's not rotating. If this were to break, if this were to snap that cable, then it would begin to rotate in a clockwise direction, but it's not doing that, so it's an equilibrium rotationally, and it's not moving up or down, so it's an equilibrium translationally. That means these two cables have to be holding up 600 newtons, up 600 newtons, up, down, up. I mean, this arrow should be longer. This represents 600 newtons. How do you know? Because there are 600 newtons of weight down. There has to be an equal and opposite force of 600 up. If there weren't, it would move. It would accelerate. If there wasn't enough force up, it would fall down. If there was more force pulling up, it would be rising up, and it's not doing that. So this is equal to that. This is 600 newtons. That angle there was 40 degrees. This is a 40-degree angle. All right. Okay. All right. So I know now the question is to figure out the tensions in the two cables. So I could figure this one out right away. This one is very much like the last problem. We have a right angle, and we want to figure out the hypotenuse from knowing the adjacent side. This angle here is going to be 50. So you could use cosine of 50, and the adjacent side 600, divide 600 by the cosine of 50, or you could use 40 and use sine for the opposite, whatever works for you. I mean, it's all good. So let's just go ahead. I'm going to stay consistent with the last video and use this angle when that adjacent side and figure out the tension here, which was tension 1. Okay, so let's see. This is the adjacent side. This is the hypotenuse. So the cosine of 50 equals my adjacent side over the tension 1, T1 equals 600 divided by the cosine of 50 degrees. And if we do that out, we'll get the tension in that first rope. So let's see what we got here. We got 600 divided by the cosine of 50, and we get 933. 933. So 933 newtons, okay, of tension pulling in this direction. Okay, it's pulling up. Now look at this cable. It's pulling the street sign not only up, but it's also pulling it over. It's pulling it to the left, to the left. Go ahead. That song's in your head now, isn't it? Yeah, you're welcome. You're welcome. So yeah, so we know what we're going to get here is another right triangle. I mean, in fact, this right triangle up here is the same as this right triangle here. But I suppose I didn't have to draw this one. I could have just stuck with this one. This is pulling up, and it's pulling over. How much is it pulling over with? has to be equal to T2. This has to be equal to T2. Well, how do you know that? Because remember, the sign isn't moving, right? So that means the up and the down are balanced. The 600 here down is balanced, the 600 up. Also, to this cable here, this T2 is pulling this thing to the right, but it's not moving to the right. Therefore, there must be an equal and opposite force to the left balancing it. So this to the right pole has got to be balanced by a to the left pole that's equal to it. So this side of the triangle is going to be equal to the T2, the tension in that second cable pulling it to the right. Well, what do you want to do, huh? How do you want to do it? A couple ways, more than one way to skin a cat. It's kind of gruesome if you think about it. Don't think about it. Don't think. So I'll take this first arrow. I'm going to show you that that arrow here has to be equal to that arrow here. If it wasn't equal to that arrow here, this would be moving left or right. Not, so they're equal. So I'll take that out. And so that arrow and that arrow, the same thing. Those are similar triangles. And so let's solve for this. You can use sine, cosine, or tangent function at this point. This we just figured out to be 933. My marker here is dying on me. Come on, marker, hang in there. 933. So maybe I want to go ahead and stick with the 50 degrees here and figure out the opposite side. I have the adjacent side. That would be tangent. Tangent's equal to the opposite over the adjacent. I'll set it up, and you can do whatever you want. This is America. So let's see, the cosine of 50 is equal to the opposite, T2, over the adjacent, 600. Multiply those, get T2. So T2 is equal to 600 multiplied by the cosine of 50. All right, so let's do that again. Cosine of 50 times 600, and we get 386. We'll round it to 386. So the tension here is 386 newtons. So cable 2 is pulling this way with 386. Cable 1, tension here was 933. All right, this has got to be pulling with more than just 600 because it's not only pulling it up, but it's also pulling it to the left to counterbalance that tension. Those are two force equilibrium problems. Those are forces. Things are in equilibrium, hence force equilibrium. And when you have something not moving, triangles become very important when you have more than just one cable. If we just have one cable here, I mean, certainly this would make the problem a lot easier if we just had sine, everywhere is sine. Do this, do that. Can't you read the sign? Okay, I should write music. I got good lyrics. If we just had one cable holding the sign up, it wouldn't be very stable. No wind, it'd be blowing all over the place. But if it was a nice calm day, we have this one 600 Newton sign. You have one cable holding up. It's going to be 600 newtons. It's not moving up or down, so that would be easy, right? But no, we can't make problems that easy. Life problems are not that easy. Life is not that easy, people. So here I am to teach you that lesson. All right, that wraps up those problems and the unit. And good luck on your L examination.